Hey guys, my name is Amin, and today we're going to be diving into Euler's Totient Theorem, which is a powerful result in number theory that extends for a Maxwell theorem. So before we get to the theorem, we'll understand the Euler totient function, see how to compute it, and then prove the theorem using clean argument. So to begin, the Euler totient function is written as phi of n, where phi is this symbol right here. And it counts how many integers from 1 to n are co-prime to n. So basically numbers that have no common factor with n except 1. So this is just also called the GCD, or greatest common divisor. So let's look at an example where we choose two integers, 8 and 15. See that the GCD is 1 because 8 composes of divisors 1, 2, 4, and 8, while 15 has the divisors 1, 3, 5, 15. So we see the only divisor, or the greatest common divisor that they share is 1. And this defines these two numbers as co-prime to each other. An example where two integers are not co-prime to each other is where the GCD is a value greater than 1. So if we choose two integers 8 and 12, we see their GCD is 4. Since 8 composes of 1, 2, 4, 8, and 12 is composed of 1, 2, 3, 4, 6, and 12. So the greatest common divisor is 4. The totient function basically calculates how many integers are co-prime to n that are less than n. And it's calculated using a formula where if you have n, and n is composed of primes p1 to pk raised to a certain power, then the totient of n equals to n times 1 minus 1 or p1 times 1 minus 1 or p2 all the way to 1 minus 1 or pk. So we can prove the totient function by considering two cases. In the first case is where n equals p to the k, where p is just a random prime number and k is what p is raised to the power of. So the only numbers not co-prime to n are the ones divisible by p, since we're looking for numbers that share a factor of p to the k. So p to the k over p equals to p to the k minus 1 integers that are not co-prime to p to the k, or n. So to find the integers that are co-prime to p to the k, we can just subtract the numbers that are not co-prime by the total number of integers that we have, which is p to the k. So p to the k minus p to the k minus 1 is the number of integers that are co-prime to p to the k. And we can just further factor out this p to the k term here, and this is p to the k times 1 minus 1 over p, which follows our formula from earlier. We can also prove this where n equals to multiple distinct primes. So in this case, let's look at where n equals p times q, where p and q are distinct primes. So first we can note that there are n equals pq total numbers from 1 to n. And so to find the number of integers that are not co-prime to n, we can find the number of factors of p and pq, which is just q multiples of p, the number of multiples of q and pq, which is just p multiples of q. The total number of integers that are not co-prime to n is just p plus q. But we have to subtract 1 here because we do count pq twice here. This is the number of integers that are not co-prime to n. So once again, we follow that same process of subtracting the number of integers that are not co-prime by the total number of integers that we have. So this is just pq minus the quantity of p plus q minus 1. And you can simplify this to get pq minus p minus q plus 1, which factors out as p minus 1 times q minus 1. So this is totient of pq as well, by the way. So this value represents the number of integers that are co-prime to pq. And we can further write this as pq times p minus 1 over p times q minus 1 over q. And if we cancel out these terms, you see that our original expression, or our value, is still maintained. So totient of n or pq is also equal to this value. And we can further say that this value is pq times 1 minus 1 over p times 1 minus 1 or cubed. And if you use common denominator, you can see that these values are actually equal to each other. This is still totient of n. So that proves the totient function and the formula that I showed earlier. And this logic can extend to any integer n with distinct prime factors. So let's move on to Euler's totient theorem and its proof. So the totient theorem states that if we have two integers that are co-prime to each other, a and n, or essentially their GCD is equal to 1, then a raised to the power of 5n is congruent to 1 mod n. To prove this, we use the concept of a reduced residue system, and this is simply the set of all integers between 1 and n that are co-prime to n. So for example, when n equals 10, the reduced residue system is r equals to elements of 1, 3, 7, and 9. An important fact is that if we take this set and multiply every element by number a that's co-prime to n, where n equals 10 in this case, and then reduce each product modulo n, or mod 10, then we get a new set of numbers that's just a rearrangement or a permutation of our original set. So if we multiply r by a equals 3, because, for example, 3 is co-prime to 10, then we see that 3r equals to 3917, because 1 times 3 is 3 mod 10, 3 times 3 is 9 mod 10, 7 times 3 equals 21, and 21 is 1 mod 10, and 9 times 3 equals 27, and 27 is 7 mod 10. So we see that this set is the same as the second set, and they're just in a different order, but still congruent to each other, mod 10. So we can expand this logic to where we have a set R that consists of elements R1 all the way till R phi n, and this is where we take the reduced residue system mod n. So if we multiply each element by the integer that's co-prime to n, which is a, then we see that a times r is just each element of the set multiplied by a, all the way until r phi n. So since this is still the reduced residue system mod n, we can see that the right-hand side, both sets are congruent to each other mod n. So r is congruent to a times r mod n. So we can substitute the values of r on both sides here and see that r1 times r2 all the way to r phi n is congruent to a times r1 times a times r2 all the way till a times r phi n. And we can just cancel out all these r terms on both sides. And so we see we have phi n number of a's on the right side here. And when we multiply them together, we see that a to the power of phi n is congruent to 1 mod n. And so this proves Euler's totient theorem, where a and n are two numbers co-prime to each other, or GCD equals to 1, and a to the power of phi n is congruent to 1 mod n. So let's solve a problem using Euler's totient theorem. So the problem reads, how many different remainders can result when the 100th power of an integer is divided by 125? So first, let's call this integer, or here, n. So we can consider two cases here. The first case where n is co-prime to 125 and where n is not co-prime to 125. So our first case is where n is co-prime to 125, and this just means that they both don't share any divisors greater than 1, so their GCD is 1. So we can say that n to the power of totient 125 is congruent to 1 mod 125, and you can calculate totient 125 here on the side, which is 125 times 1 minus 1 over 5, which equals to 125 times 4 over 5, which equals to 100. So n to the power of 100 is congruent to 1 mod 125. This is convenient for us because we're looking at the remainders that can result when the 100th power of an integer n is divided by 125. So we see the only remainder that occurs here is 1. So when n is co-prime to 125, the remainder that results is 1. So our second case is where n is not co-prime to 125. And so this means that n must have a factor of 5 in its prime factorization, because 125 is just 5 to the power of 3. So if n is not co-prime to 125 and their GCD is greater than 1, then that means that n shares a factor of 5, or multiple factors of 5. So we know n is just 5 times x, where x is just some random integer. And so since the problem is still asking the remainder of n to the power of 100 divided by 125, we take n to the power of 100, which is also 5x to the power of 100 mod 125, and we distribute, we get 5 to the power of 100 times x to the power of 100 mod 125. It's going to go into n to the power of 100. So we can further write this as 5 to the 3 times 5 to the 97 times x to the 100 mod 125. And we can notice here that 5 to the 3 is just 125. And 125 is being multiplied by 5 to the 97 times x to the 100. So this is just some random integer. So when 125 is multiplied by some integer, then we know that it is 0 mod 125 because it still has that factor of 125. That means n to the power of 100 has a factor of 125. So n to the power of 100 is just 0 mod 125. So we see that when n is not co-prime to 125, our remainder here is 0. But when n is co-prime to 125, our remainder here is 1. So we get two different remainders for two different cases. So since the question asks how many different remainders can result, our answer is 2. And so Euler's Totient Theorem is a really useful theorem and a powerful theorem, especially when we're doing modular arithmetic, and it can really help us solve problems in a fast way and in a clean way.